In Chapter 5, we're going to learn alkene reactions. So we're going to learn different reaction mechanisms, and that will show us how reactants go all the way to products in all of the intermediate steps. So in this first part, we're going to study some of the basics that you need to understand before you can tackle full-blown mechanisms. We're going to start by looking at something called polar reactions. Another name for polar reactions are called ionic reactions. And your goal is that you can predict the products for these reactions. And also, in addition to predicting products, you'll also be able to predict reactants if you are given one reactant and then a product and you want to figure out what the missing reactants are. Polar reactions result from the force of attraction between opposite charges. We know that positive and negative charges attract, whereas like charges repel. And ionic reactions will also be guided by the octet rule. Two important terms to understand are nucleophiles and electrophiles. Nucleophiles are species that are nucleus-loving, whereas electrophiles are species that are electron-loving. And so when we look at molecules, we want to think about the overall polarity of that molecule and the electronegativity of the atoms in order to figure out if something would be attracted to a positive nucleus or if it would be attracted to negative electrons. So in the first molecule on the left, we have a partially negative chlorine that is bonded to carbon, which would be partially positive since chlorine is more electronegative. So what that means is that the carbon-chlorine bond is going to be a polar bond. So that's what this dipole arrow represents. And our carbon will end up having a partial positive charge. Now on the molecule on the right, we have carbon in the middle again, but this time lithium is bonded to carbon. And lithium would end up being partially positive, which would force carbon to be partially negative. And so notice our dipole arrow in this example is going in the opposite direction. So when we look at carbon in each of these cases and think about how would these molecules react based upon the partial charge of carbon, we can call the carbon on the left-hand side an electrophile or an electrophilic carbon. Because that carbon has a partial positive charge on it, that carbon is going to be attracted to electrophiles or nucleophiles, some other species that is partially positive. And comparing that with the molecule on the right, that carbon has a partial negative charge. And so we could say that that carbon is nucleophilic or nucleus-loving. So it's going to be attracted to a positive nucleus. So when you are determining if something is an electrophile or a nucleophile, you're thinking about what it would be attracted to. Electrophiles are positively charged species that are attracted to negatively charged electrons, whereas nucleophiles are negatively charged species that are attracted to positively charged electrophiles. So nucleophiles and electrophiles always react with one another. So just to reiterate what we said, nucleophile is an electron-rich center. You can think about it like a nucleus lover, and the nucleus is a positively charged area. An electrophile is an electron-deficient center for some reason, or something that has a positive charge on it. It's going to be an electron lover. Electrons have a negative charge. And nucleophiles always react with electrophiles. So nucleophiles are where the electrons are at. They're the species that are negatively charged that have electrons. And so they're going to attack electrophiles, which are electrophiles are the species that are going to have a partial positive charge, or they're going to be an electron deficient center. So we always start where our electrons are located at, and our electrons are going to be on our nucleophiles. If you recall our definition for Lewis bases, a Lewis base was an electron pair donor. A nucleophile is essentially synonymous with the definition for a Lewis base. So let's look at a couple examples of what possible nucleophiles could be so you can start identifying them. So an example on the far left, we have ethoxide, which this is an alkoxide anion. And so here we have 3 lone pairs of electrons. That oxygen has a -1 formal charge. So this is going to be a nucleophile. It's going to be attracted to a positive nucleus. So one pair of those electrons could get donated to some other electrophilic center. So that arrow is not pointing to anything, but later it will point to something specific. So it could be a negatively charged molecule. That's pretty common for a nucleophile. It could also be a neutral molecule, no charge. So something like ethanol could also function as a nucleophile. It wouldn't be as strong as ethoxide because ethoxide has a negative charge, but ethanol does have 2 lone pairs of electrons, so it could donate one of those lone pairs of electrons to an electrophile. So let's just pretend that each of these are attacking some generic electrophile, which we'll call E+ right now. So both of those could function as nucleophiles. Another example that we'll see in this chapter covering alkene reactions first is something that has a set of pi electrons that it can donate. So the pi electrons in something like an alkene can attack, they can function as a nucleophile, and they can attack an electrophile. And these are the type of reactions we'll start out by looking at. So those pi electrons right there, those pi electrons are held above and below that planar alkene, and so they're less loosely held than the sigma electrons of the double bond, and they're more available for attacking. Another concept that comes up when we start looking at mechanisms is polarizability. So polarizability is the ability of an atom to distribute its electron density unevenly in response to external influences. And this just kind of comes into play sometimes when we start looking at molecules that are overall nonpolar, but they can become slightly polarized due to other factors, such as an induced dipole happening and then causing the electrons to shift from one side to another. Polarizability can determine how strong a certain nucleophile is, and it's dependent upon the size of an atom and how many electrons are far away from the nucleus. Next, we'll look at a couple examples of some electrophiles or electrophilic centers. So electrophiles are pretty much synonymous with Lewis acids. And if you recall, the definition for a Lewis acid is an electron pair acceptor. So electrophiles love electrons. They will react with nucleophiles. And so in order for a nucleophile to attack an electrophile, it has to be able to accept the extra electrons from that nucleophile. So usually it's something that might have a positive charge, partial positive or full positive charge that will allow it to accept those extra electrons in some way. So in the first molecule on the left, we have a carbon that has a partial positive charge, and the chlorine halogen has a partial negative charge. So specifically on that whole molecule, which if we name it, it would be 1, 2, 3, 4, we have 1-chlorobutane. The whole molecule we could say is an electrophile, but the whole molecule isn't where we're honing in on. We're looking at a very specific site of that molecule, and it's the carbon at position number 1 that is the electrophilic center. That's the location of the positive charge, and that's where a nucleophile is going to attack. Next to that, we have a carbocation, so that has a full positive formal charge on that carbon. And so we could label the whole molecule our electrophile, but really we want to know that that carbon that is the carbocation, that is going to be the location of attack for a nucleophile. So some nucleophile, we'll denote that with Nu negative because nucleophiles have electrons, will attack that electrophilic center, which is our location that is most positive in the electrophile. When we have something like a carbocation, those are planar molecules. That carbon of that carbocation is sp2 hybridized, and it has an empty p orbital that sits above and below the axis, the plane there, the plane of the page you can imagine in. So that's going to have some considerations when we start looking at reactions, because a nucleophile could technically attack above the plane, or it has a 50-50 chance of attacking from below the plane there. So there's different things that we want to consider when we start looking at the mechanisms in the products that we can form. So this is just a little summary chart of some common nucleophilic and electrophilic centers. You could have a carbon, if we look at the nucleophiles, that has inductive effects where electrons are either being pushed towards or pulled away from a certain center. So that carbon in our example had a partial negative charge because it would have the electrons closer to it since it's more electronegative than lithium, for example. You could have a lone pair of electrons. So in this example, the oxygen has lone pairs of electrons that it could donate. Or you could have something like a pi bond. All of those can function as nucleophiles. The pi bond can attack an electrophile, the lone pair of electrons can attack an electrophile, and even this carbon can attack an electrophile because it's partially negative. Electrophiles, we looked at a couple of those. They can have an empty p orbital, so something like a carbocation. Or you could have a carbon or some other atom that has a partial positive charge due to inductive effects, due to that polarity of that bond. So in this case, the electronegative chlorine is pulling those electrons away from our carbon, making that susceptible to attack from some nucleophile. Let's practice labeling the nucleophilic and electrophilic sites on this molecule here. So let's first start with the nucleophilic sites. We'll use red for those. So a nucleophile is a species that is electron rich and is attracted to a nucleus essentially. And so we are looking for having lone pairs of electrons. You're looking for maybe a negative charge. You could have pi electrons that could be donated. Or you could have a difference in electronegativity where a certain atom is more electronegative due to inductive effects or due to the polarity of that bond overall. So if we start on the left, we have an oxygen right here, and it has two lone pairs of electrons. So technically, that could be a nucleophilic site, and it would specifically be the oxygen that would be donating those electrons. Here we have a nitrogen that has a lone pair of electrons on it. That nitrogen could function as a nucleophile and donate its electrons. This oxygen right here has two lone pairs of electrons. That could possibly function as a nucleophile. Our oxygen at the end, they're not labeled, but there would actually be three lone pairs of electrons there. And so that oxygen has a -1 formal charge. That could donate its electrons. Now, our oxygen with the positive charge, that most likely would not be acting as a nucleophile, even though it does have one lone pair of electrons on it. But because it already has a positive formal charge, it's going to want to get rid of that formal charge, and it would become more positive if it formed another bond. So that's going to not act as a nucleophile in this case. So those would be our nucleophilic sites. Now looking for electrophilic sites, electrophiles are going to be species that are attracted to electrons. So we denote that as E+ because they are partial positive or there's a positive formal charge on them. They want to be attacked by other nucleophiles. So electrophiles could be something like this carbon right here. This could be an electrophilic carbon because it is partially positive and the oxygen it's bonded to is partially negative. So this would be an electrophilic site. We could say the same thing about this carbon right here. This carbon right here could be an electrophilic site. It's partially positive. The oxygen it's bonded to is partially negative. And we missed actually one more nucleophilic site. These pi electrons of our double bond right here could function as a nucleophile and attack an electrophile. So those were our pi electrons. So those are just some examples of nucleophilic and electrophilic sites in the same molecule. But usually they will be on two different molecules. One molecule will be more nucleophilic and one molecule will be more electrophilic, and they'll react together. So this was just kind of a made-up imaginary problem. I just want to remind you what we've previously learned about arrows. When you draw an arrow, what you are showing is the flow of electrons. And so every arrow that you draw represents 2 electrons. When you draw an arrow that has a full head, such as the ones that we will be drawing, there are other arrows that you can see that look like this that have half of an arrowhead, and those are used for radical reactions. and those represent the transfer of one electron. So we'll cover radical reactions and maybe look at some of those types of mechanisms at some point, but usually most of the time you're going to be drawing arrows that have a tail end and they have a head end, and the head has a full head there, not a half of one. And so that represents the transfer of two electrons, and they show where they're starting at, which is the tail, and where they're heading towards, which is the head. So they should end at the substance that is accepting those electrons, and they should start at the substance that has the electrons to give. So using a little bit of our new terminology, so we would have looked at this mini mechanism when we were looking at Bronsted-Lowry acids and bases, but imagine instead of we call this a base now, we call it a nucleophile. It's an electron-rich species that's attached to an electrophile. And now between H and A, let's imagine, our hydrogen would be partially positive and A could be partially negative. So this molecule would be in our electrophile, and the hydrogen would be the electrophilic site. So maybe our base donates its pair of electrons to our hydrogen, and then that bond breaks, that covalent bond between H and A, and those two electrons stay with A, and we formed our new BH bond. So those two electrons there are now in between B and H. And A has a negative formal charge because it was left with those two electrons that were in the covalent bond when it broke. So this is just a quick reminder of using curved arrows. We're going to use them all throughout this semester and the next in order to draw mechanisms. The type of reaction that we're going to start by learning is called an electrophilic addition reaction. Sometimes this is abbreviated as EAR for short. So alkenes are electron-rich nucleophiles. The pi bond of the alkene specifically is the nucleophile of that alkene, and so they can react with a lot of various electrophiles. And so we'll be looking at different reactions where we essentially change the electrophile usually, and the alkene will act as the nucleophile and attack that electrophile. An alkene, we learned, also has 1 degree of unsaturation, and so they can accommodate other atoms around them once that double bond breaks, where the pi bond is held. And so that's why it's referred to as an addition reaction, because you're adding something across the double bond is how we would describe that. So imagine on the left, if we have our reactants over here, we have some generic alkene, and we're specifically looking at the pi electrons, which is the double bond there, the pi bond, and we're adding some substance. This is just made up, XY. So we're going to have to break the sigma bond of XY to add it, and we're going to have to break the pi bond of the alkene to add it. And when we form our products are where we have added X and Y across that double bond. So now notice we formed a new bond here from 1 carbon to X, new bond here from 1 carbon to Y. And we no longer have the pi bond in between our two original carbons. So these would represent those original carbons there. These two methyl groups that were on each side to start with are still there, but now we've changed our sp2 carbons because it was a double bond. Now they are sp3 carbons and they have 4 single bonds to them. So we made 2 sigma bonds and we broke a sigma bond and a pi bond. So that's kind of the common theme with an addition reaction that you'll see is you're adding something across that double bond. And how the mechanisms and the reactions will change will depend upon what you are adding across and what side something will go to and what's going to be more stable. So we're going to have to look at a lot of different little intricacies, but this is the general gist of an overall alkene addition reaction. And just to point out a little terminology thing that you might see, an alkene, the pi electrons of that alkene, when they act as a nucleophile, that means that they are attacking an electrophile. So those pi electrons right here, those loosely held pi electrons above and below the sigma bond, the internuclear axis, if they attack an electrophile or something that is electron deficient, then they are functioning as a nucleophile. If the double bond, the pi electrons of the double bond, attacks a proton, on the other hand, we describe it reacting as a base instead of a nucleophile. But essentially, it's doing the same thing. It's just that if it's specifically attacking a hydrogen ion, in other words, a proton, then it's functioning as a base. So that's just a distinction that's used throughout pretty much all of organic chemistry, whether we call something a nucleophile versus call it a base. The first reaction we'll take a look at is one of the simplest alkene addition reactions, and it's called hydrohalogenation. So the name really gives you a hint as to what is being added across the double bond. So hydro typically refers to hydrogen. Halo refers to a halogen. And then genation just is, that's kind of added at the end. That's the full name of the reaction. So we have hydrohalogenation. We're adding a hydrogen to one side and a halogen to the other. So some example of hydrogen halides, you could have HF, you could have HCl, HBr, HI. Those are all just example of hydrogen halides. And any one of those could technically add across the double bond of an alkene. And so if we look at a given alkene, so here we have 2-butene, so I'm going to redraw this in line bond structure. 2 indicates the position of our double bond, and it doesn't really matter right now if it's E or Z. So it could look like that, or it could look like that. The one on the left we know is Z. The groups, the high priority groups, are on Z, same side. The alkene on the right that I drew, that would be our E stereoisomer, where the high priority groups are on opposite sides. So either way, whether we're looking at the Z or E stereoisomer of 2-butene, let's imagine what our product would be if we added HBr across the double bond. So on one side, we're going to add a hydrogen. So attached to this carbon, maybe we add our hydrogen. And then to the other carbon, we're going to add the bromo group, the halogen. And since 2-butene is symmetrical, we don't have to think about what side is going to take the hydrogen yet and what side is going to take the bromo group yet. We're just saying that each of those groups gets added across that double bond. The pi bond goes away, it gets broken, and we form those 2 new sigma bonds at the locations at the end of where that double bond would have been. So here's our product. We have a hydrogen there on this carbon, and we have our bromo group on this carbon. So drawing this in line bond structure, we would have that, and then we have a new bond to bromo. We technically don't even have to show the hydrogen because we don't show hydrogens on line bond structure, but I'll draw it up here just so we can see that it was added across the double bond. And so that was me starting with the E stereoisomer. And our product here then would be 2-bromobutane. So notice we have 1, 2, 3, 4 carbons, and the bromo group is at position number 2. So our product is an alkyl halide. Specifically, we have a secondary alkyl halide. The hydrohalogenation reaction is said to be regioselective, or it has regioselectivity. And what that means is when you have more than one possible place that you could put a certain group that you're adding across the double bond, and one product forms over the other, it's a regioselective reaction. So, for example, if we have an unsymmetrical alkene, unlike we just saw previously with 2-butene, now we have an alkene where one side is more substituted and the other side is less substituted. So on the right, the more substituted side, that's more substituted because it has 2 alkyl groups coming off of it. So I'm just counting the number of groups coming off of the double bond, off of this position right here that's highlighted in green. The less substituted side has only 1 alkyl group coming off. So now when we look at the product that's formed with an unsymmetrical alkene, notice where the hydrogen group gets placed and where the bromo group gets placed when added across the double bond. The bromo group got placed on the most substituted or more substituted position. The hydrogen got placed on the less substituted position. So this is a regioselective reaction. There is a preference essentially for where certain groups that are getting added across the double bond get placed. And this is going to be the case for any hydrohalogenation reaction that we look at. It doesn't just have to be HBr, it could be HCl or HI. The halogen is always going to be placed on the more substituted side. And the hydrogen will always end up on the least substituted side. And we'll talk about why that is in a moment. So before we get into the whys, let's look at a couple examples. If we have one hexene plus HCl, what's our product going to be? So if we draw 1, 2, 3, 4, 5, 6, and then one hexene means that the double bond is at position number 1, and we're reacting with HCl. So we know that our hydrohalogen is HCl, so we're going to add hydrogen to one side and a chloro group to the other side. We have to decide where those groups are going to go. We know we're going to break the bond that's in between hydrogen and chlorine, and we're going to break the pi bond. So what we're going to form are two new sigma bonds, and we're going to place our hydrogen on the least substituted side and our chloro group on the more substituted side. So if we look at our 1-hexene, the end, which is the terminal location, is going to be our least substituted side. There's two hydrogens coming off there and no alkyl groups. Off of the carbon at the top, that's going to be our more or most substituted side. Here we have one alkyl group coming off of the double bond from that side. So when we place our chloro group, we're going to place our chloro group coming off of where the most substituted side was. And if we want to show our hydrogen, we can do that. So we still would have the two hydrogens there from before. We just don't normally show them. And then that hydrogen that we added from the HCl. So our new product that we make would be 2-chlorohexane. So now we have to change the suffix to ane because we have an alkane and not an alkene product anymore. When we follow the regioselectivity of the reaction, where we place the halogen on the more substituted side and the hydrogen on the least substituted side, this is referred to as Markovnikov's rule. And so basically that says exactly what we've been saying. The halogen goes on the carbon with the greater number of alkyl substituents, and that's going to be because that's where it's the most stable. So this is considered to be a Markovnikov reaction because this reaction follows that general rule of stability. So let's try a couple more examples here. We have 2-methylpropene. So propene is going to have 3 carbons. We're going to have a methyl group at position number 2. Our reaction is with HCl. So when we decide where we're going to place them, we're going to put our chloro group on the most substituted side, which that's going to be on the left of this one that I drew. And the hydrogen is going to go to the least substituted side. So our product, we're going to have a chloro group here, and then we added another hydrogen that's hanging out with now the other two at the end. Lastly, we have 1-methylcyclohexene. So we have a cycloalkene. So we're going to have 6 carbons. And then at position number 1, there's a methyl group coming off. And we have HBr. So when we're deciding what side is going to get the hydrogen, what side is going to get the bromo group, our most substituted side of the double bond is the one with the methyl group coming off. And our least substituted side is the one that does not have the methyl group coming off. So technically, since it's in a ring, it's a little bit different when you look at it. This one, at this least position, just has considered one alkyl group on that side that's attached there. Whereas at the most substitute position, we could go towards the methyl group or we could go towards the ring. So it's like there's 2 alkyl groups on that side. So our product then, we would have our cyclohexane ring. We don't have our pi bond there anymore. Our methyl group's still there. We added a bromo group at that position, and then we added a hydrogen up there. There was already one hydrogen there that was unwritten, so now there's two. So this is Markovnikov's rule, where the halogen goes to the side that has the greater number of substituents. The reason that the hydrohalogenation reaction and many other alkene addition reactions go through Markovnikov's rule and have regiochemistry is due to intermediates that they form throughout the reaction. And so one common intermediate that you'll see a lot is the carbocation. So we have to be able to understand carbocation stability to assess what intermediates are more stable than others. And so this reaction does not occur in one step. It actually occurs in two steps that happen one after the other. And that's what leads to that regioselectivity that we see. So carbocations are formed as reactive intermediates. And you might recall we talked about reactive intermediates back in Chem 112 when we were learning some basic mechanisms and activation energy and catalysts, and we drew potential energy diagrams. So reactive intermediates were species that were essentially formed in one step of a reaction and used up in another step. And that's no different here. So they are species that are fleeting. They're formed and then they're used up basically as soon as they're formed. So it's rapid how fast they're used up. They don't accumulate. You can't isolate a reactive intermediate. So carbocation is a common reactive intermediate, and some carbocations will be more stable than others. And so that will determine the reaction's regioselectivity. Carbocations are classified by the degree of alkyl substitution at that electron deficient carbon center, so the carbon that has the positive formal charge. Carbocations are stabilized by something called inductive effects, which inductive effects are the donation of electrons by alkyl groups through sigma bonds to that empty p orbital of the carbocation. So basically, the more number of alkyl groups that you have around that positive charged carbon there, the more possibility for donation towards that carbon, and the more we can stabilize that positive formal charge. So if you have a methyl carbocation, you don't have any alkyl groups attached. You just have 3 hydrogens there. And so that is going to be your least stable carbocation, is having a methyl one. In fact, they hardly exist. It's so unstable. A primary carbocation has 1 alkyl group attached. And so imagine these electrons in that sigma bond being pushed towards the positive carbocation. Well, if electrons, which are negative, can be pushed towards that positive carbocation, they can help stabilize it. But in a primary carbocation, you only have 1 R group doing the stabilizing. In a secondary carbocation, you've got 2 R groups, 2 generic alkyl groups that can push their electron density back towards that positive charge on carbon. And then the most stable carbocation is a tertiary carbocation. You have 3 R groups attached to your carbocation, 3 opportunities for electron density to be pushed back towards there via inductive effects. So you got your most stable as tertiary, your least stable as methyl. Another phenomenon that stabilizes carbocations is called hyperconjugation. So they are stabilized by inductive effects and hyperconjugation. Hyperconjugation is a little different. It's the overlap of bonding electrons from adjacent sigma bonds with the empty p orbital of the carbocation. So we have essentially alkyl groups that are bonded through sigma bonds to your neighboring carbocation, and their electrons can donate through space towards that empty p orbital. So imagine that you have a methyl group and it's bonded to our carbocation right here. That's a stabilizing factor. It does stabilize through inductive effects, so the electrons in that sigma bond push back towards that carbon, but also Imagine that methyl group. If we were to draw that methyl group out, it's a carbon, and then off of that carbon is 3 hydrogens there. So that's what it really looks like that's attached there. So any one of those hydrogens that are sigma bonded to the carbon, so all of these sigma bonds right here, can share their electron density with the empty p orbital. So that's what this is showing right here, is the overlap of that electron density between that sigma bond and our empty p orbital on our carbocation. So that's hyperconjugation, and that's another stabilizing factor that will make your carbocation more stable. So the more opportunities for hyperconjugation, the more stable the carbocation, and the more opportunities for inductive effects to occur, the more stable that carbocation will be as well. Next, we're going to try to draw the basic mechanism for a hydrohalogenation reaction. So what is a mechanism when we say that word? What we're talking about is the complete description of a reaction pathway, including any reactive intermediates. That is the mechanism. Sometimes they also include something called a transition state. You might remember from Chem 112, a transition state was abbreviated like this, and it was a high energy state that formed during a reaction. And so it was that highest point on the potential energy diagram along the curve. So that was where our transition state was, and it was where we had a species that was formed with partially broken and partially formed bonds, and it could fall down the hill to make products, or it could fall down the hill back this way to go back to reactants. So when we're drawing a mechanism, we use our arrows to show the flow of electrons. We draw reactive intermediates that are involved. We show transition states. We show all formal charges. So there's a lot that goes into them, and we're definitely going to start with some of the most basic mechanisms and then work our way up. So let's look at our hydrohalogenation mechanism, and specifically this is called a hydrobromination because our reactant is HBr. So right now we're just starting with a generic alkene. This alkene could be any alkene, but we're just starting with an alkene that is unsymmetrical, so we can choose what side our halogen is going to get added to and what side our hydrogen is going to get added to. So we know that our alkene is electron rich. It's electron rich, and so our alkene is going to function as our nucleophile, specifically those pi electrons of our alkene. And then HBr, if we analyze that reactant, that's going to have to function as our electrophile. Specifically, the hydrogen is going to be partially positive, it's less electronegative. The bromine is going to be partially negative, it's more electronegative. So what atom is our pi electrons going to want to attack on our electrophile? They're electron rich, they're going to want to attack our most electron deficient location, which is the hydrogen. So we're going to start with our pi electrons. We start drawing our arrow there. We point them towards the hydrogen. So those pi electrons are attacking hydrogen. And when they do, the covalent bond between hydrogen and bromine breaks. So those electrons go to the bromine. Notice that we have clear beginnings or origins, and we have clear destinations, which are our endpoints. You can read exactly where my arrow is starting and where it's pointing to. That's really important when you're writing a mechanism, is that the arrows are neat and can be followed from beginning to end, because that is actually what's being graded, is not just what you draw for your molecules, but your arrows. So when this happens, we can do one of two things. We're going to break that pi bond. So that pi bond's broken, and we have to decide what side are we going to put hydrogen on. So we'll draw another arrow here. We could go to the top molecule, or we could go to the bottom molecule. So if we put hydrogen on this position, then our carbocation would develop over here on the left-hand side. If we were to put hydrogen on the opposite side, then our carbocation would develop right here. So we have a carbocation because we broke that pi bond and hydrogen just went to one side first. And so the opposite side of whatever side hydrogen's not on is now electron deficient. It doesn't have 4 bonds around that carbon center, and so there's a positive charge. There's a carbocation that's formed. And so what we just learned about our carbocations is that the greater number of alkyl groups around that carbocation stabilize it more. And so notice on the bottom one, we have one alkyl group here, and then this whole thing would be an alkyl group there. So in this case, that's a secondary carbocation that's formed. Versus on the top, that top one is a tertiary carbocation. So what's not going to form when we have the choice is the more unstable secondary carbocation. So using Markovnikov's rule, the hydrogen's going to go to the least substituted side. So this is our least substituted side. This is our most substituted side. So the carbocation actually ends up on the more substituted side since hydrogen is on the least. So this arrow is not going to happen. You don't even have to show the formation of this secondary carbocation, but that was just to walk you through the analysis of why we do not end up with hydrogen on the most substituted side. It's because that carbocation is less stable than the tertiary carbocation. So the mechanism goes through the tertiary carbocation intermediate. So that's the first step, is forming that carbocation. And next we have our bromide anion that was formed when we broke our hydrogen bromine sigma bond in step 1. So our bromide will attack that carbocation, and this is once again a situation of negative attacking positive. So our negative bromide acts as a nucleophile. Nucleophiles attack electrophiles. Our carbocation is an electrophile. So we're going to attack that electrophile and form a new bond there. And there's nothing that has to break or anything because that carbocation is already electron deficient. It has only 6 electrons bonded to it. It doesn't have a complete octet. So by forming this new bond, we complete the octet at that position. So we have a new bond between carbon and bromine formed here. Our other new bond was between that least substituted carbon and the hydrogen. And so in this case, that would be our product. Now, something to point out is you're not always going to have a tertiary carbocation. This was just a generic alkene that I started you with. You could have all kinds of different alkenes that you do for your reactions. And maybe you have a secondary carbocation versus a primary carbocation. Well, then in that case, the reaction will go through the secondary carbocation because that one's more stable. So you have to analyze essentially what intermediate you could form and pick the more stable one. But in each case, the halogen ends up on the more substituted side and the hydrogen ends up on the least substituted side in your product. So just to make sure to drill the point home, let's try the mechanism again, but we're going to draw it for a hydrochlorination. So now we're reacting our just generic alkene with HCl instead of HBr, but it's the same process. So our alkene acts as a nucleophile. It's electron rich. It's going to attack our hydrogen, which is partially positive because chlorine will be partially negative as it's more electronegative. So our nucleophilic alkene will attack our hydrogen. The bond between hydrogen and chlorine will break. The electrons will stay with chlorine, forming chloride ion to be used in the second step. In the first step, we're going to go through the more stable carbocation intermediate, which is the tertiary carbocation that's formed. Our hydrogen got added to the least substituted side. Our chloride now is going to function as a nucleophile and attack our tertiary carbocation, which is an electrophile. And we formed a new bond between our carbon and our chlorine. So in this case, we have our alkyl halide, which is always going to be our product when we undergo our hydrohalogenation reaction. So in this example, we formed a tertiary alkyl halide because we went through a tertiary carbocation intermediate. So when you're learning mechanisms, I highly recommend that you draw every step. I have kind of an outline on the slides with the products and reactants already drawn in just to keep everything neat for your notes and so we can follow along in a more organized fashion. But you should practice drawing all the molecules, drawing in the formal charges, drawing the new bonds, understanding where they're broken. You want to be able to go through each step to be able to get all the way from reactants to products and show all of the arrows and all of the intermediates in between. So this is just a two-step mechanism, but it'll get more complicated when there's more and more steps.